There's just something mesmerizing about fire, isn't there? Whether you're watching a campfire or just a single candle flame, we're totally drawn to its warmth and light. But what's actually happening inside that flicker? Well, it's a powerful chemical reaction called combustion, and today we're going to break down the science behind it.
I mean, it seems so simple, right? But this one single chemical reaction has literally shaped the course of human civilization. So yeah, let's get to the bottom of what's really going on when something burns.
Okay, at its absolute core, here's the scientific definition. Combustion is just a chemical process where a substance reacts really fast with oxygen to give off heat and light. But that simple definition, well, it unlocks a whole fascinating world of science, starting with the most obvious question.
Right, so let's start with the part we can all see, the flame itself. What exactly is that thing?
A flame is the visible, gaseous part of a fire. It happens when a fuel gets hot enough to vaporize, to turn into a gas, before it actually burns. The perfect example is a candle. The wax melts, gets sucked up the wick, turns into a vapor, and that vapor is what's on fire. Now, compare that to something like charcoal. It doesn't really turn into a gas. It just kind of burns on the surface. That's why it glows instead of producing a tall, flickering flame.
Now here's where it gets really interesting. You can't just have a fire without a few key ingredients. Seriously, you should think of it like a recipe. If you're missing even one component, nothing happens.
And here they are. This is what's famously called the fire triangle. First, you need fuel, the thing that's actually going to burn. Second, you need air, or more specifically, the oxygen in the air. And third, you need enough heat to get the whole reaction started. Take away just one of those three things, and the fire goes out.
So the need for fuel and heat, that seems kind of obvious, right? But just how critical is that constant supply of air? Well, a classic little experiment with a candle and a chimney shows this perfectly. So check this out. In the first step, with an open chimney, air flows in freely from the bottom and the candle burns bright and steady. But the second you block that airflow, look what happens. The flame starts to flicker, it gets all smoky, it's literally starving for oxygen. And finally, if you cut off its air supply completely by covering the top, the flame is snuffed out. It's the perfect demonstration. No air, no fire. All right, let's talk about that third ingredient, heat. Every fuel has a specific ignition temperature, and it's exactly what it sounds like. It's the absolute lowest temperature a substance needs to reach before it will catch fire. I mean, a piece of paper catches fire almost instantly with a match, but a big log needs a lot more sustained heat, right? That's just because paper has a much lower ignition temperature. Okay, so keeping that idea in mind, here is a fun little puzzle for you. We all know paper is super flammable. Its ignition temperature is really low. So how in the world is it possible to boil water in a paper cup over an open flame without the cup just bursting into fire? The secret is the water itself. See, water is fantastic at absorbing heat. As the flame heats the paper cup, the water inside is constantly pulling that heat away, which means the paper itself never gets hot enough to reach its ignition temperature. It just can't get hot enough to burn. Now, understanding this recipe for fire isn't just a fun science lesson. It's the fundamental principle behind how we control it. In fact, this knowledge is the entire basis for how we fight fires. This is the #1 rule of firefighting. Every single method, from a simple bucket of water to a super sophisticated fire extinguisher, works by attacking one side of that fire triangle we talked about. You either remove the heat, remove the air, or remove the fuel. Let's look at two common methods. Water is great for things like burning wood or paper because it attacks the heat part of the triangle. It just cools the fuel down below its ignition point. But a carbon dioxide extinguisher works in a totally different way. It attacks the air side. CO2 gas is heavier than oxygen, so it sinks down and literally smothers the fire in a blanket of gas, cutting off its oxygen supply. That makes it perfect for fires where water would be super dangerous. And this is why you never ever use water on just any fire. If you throw water on an electrical fire, it can conduct electricity right back to you, which is incredibly dangerous. And with an oil fire, the water is heavier, so it sinks to the bottom, pushing all that burning oil up and out, which can make things so much worse. Now, not all combustion is the same. The reaction can happen at different speeds and in different ways, and that leads to some very different results. I mean, just look at the variety here. You've got rapid combustion, which is what we're all familiar with, like lighting a gas stove. Then you have spontaneous combustion, where a material can actually heat itself up to its own ignition point,
like a pile of oily rags or coal dust in a mine. And then there's an explosion, which is just combustion that happens so ridiculously fast that it releases a massive amount of energy, heat, light, and sound all at once.
So, if we zoom out, it's really impossible to overstate how much combustion has built our modern world. I mean, from our power plants to our cars, we basically run on fire. But that comes with a cost.
To compare different fuels, we need a way to measure their energy output. We do this with something called calorific value. You can think of it like the miles per gallon for fuel. It tells us exactly how much heat energy we get from burning 1 kilogram of a substance. And just look at the difference. Wood gives off a pretty decent amount of energy. Petrol, well, it more than doubles that. But then look at hydrogen. It packs an incredible amount of energy into the same mass. This is exactly why we're always searching for fuels with a higher and higher calorific value. But here's the catch. Getting all that energy has consequences. Burning fuels, especially the carbon-based ones we rely on, like coal, oil, and gas, releases a whole lot of stuff into the atmosphere besides just heat.
And these byproducts are a huge problem. We get unburnt carbon particles, soot, that cause respiratory diseases. We get poisonous carbon monoxide when things don't burn completely. We get carbon dioxide, which is a major driver of global warming. And we get sulfur and nitrogen oxides that dissolve in rain and create acid rain. This is the dark side of combustion.
This is why there's such a huge push for cleaner fuels. Compressed natural gas, or CNG, is a great example. Because its chemical makeup is simpler, when it burns, it produces far, far fewer of those harmful byproducts compared to something like gasoline or diesel.
And all this leaves us with a final, massive question. The very same chemical process that powered our Industrial Revolution and built the world we live in today is now creating some of our biggest environmental challenges. So the question for all of us really is, what comes next? How are we going to power our future?